Hello everyone. Today we're going to talk about merge sort. So far we have learned different ways of sorting numbers or some sorting arrays of values. So binary search tree, we use a binary search tree, okay, to sort numbers, and we use the in-order traversing to get numbers in a sorted way. We learned bubble sort, insertion sort, and selection sort, and now that's the time to learn merge sort. Merge sort is an effective sorting algorithm, okay, and it uses like a divide and conquer approach to sort the numbers in the array. So let's say here we have the array A with 6 numbers. So n, that is the number of values that we have, is equal to 6. So the way that the merge sort works is dividing the array that you have here, like we have an array of 6 numbers, to 2 sub problems or 2 sub arrays. So you may ask that how we can divide this array into 2 smaller problems. So the best approach is to divide the array into 2 equally sized sub arrays. So here, let's say that if we are not choosing the breakpoint to be in the middle. So let's say we are choosing 7 to be when we are dividing the subproblem. So we have a subproblem of size 1, and the other subproblem will be of size 5. So as you see, in this case, the subproblem, okay, one of the subproblem is not small enough, okay? We just made it smaller by size 1. So it's not going to help us too much. So that's why here we are trying to almost create 2 sub-arrays of the same size. And why I'm saying that almost, because sometimes it's not possible to make the array into this 2 smaller equally sized sub-arrays. So for using the merge sort, what we are going to do is we are going to use some indexes. So first of all, I have the lower index. That says that what is the very left index of my array. So that's 0, and the high that says that what's going to the right is index of my array that's equal to 5. And I have another one that says that what's the middle index? Where is the middle of the array? That here we are defining as h plus l, okay, and divided by 2. That in this case will be 5 plus 0 divided by 2. So 5 plus 0 divided by 2, and we're taking the floor of that is going to be equal to number 2. So here the index 2 will be our separating index. My first sub-array, okay, the first sub-array will be from 0, let's write it first with the formula, so it's going to be from L to medium index, and my second sub-array will be from middle index plus 1 to the high. So here my first sub-array will be from 0 to 2, and from 2 plus 1, that is 3 to 5. That says that this is my first sub-array, and this is my second sub-array. That as you see, in this case there are both equally sized. Now next we're gonna talk about how we can solve these 2 sub-problems and finally build the final solution of for this array. Okay, now we have these 2 sub-arrays, the left sub-array that is 7, 3, and 2, and the right sub-array that is 9, 4, and 8. So, similar to what we did for the first array, we're also going to do the same thing for these 2 sub-arrays, because they are not small enough still for merging the solution. Okay, we want our sub-problems to be small enough that they cannot be break down into smaller sub-problems. So let's start with the first sub-array. So we have the low index that is equal to 0, the high index equal to 2, and the middle index will be 2 plus 0 divided by 2, that is going to be 1. So our first, the left sub array will be from 0 to middle index, that's going to be, sorry about that, it's going to be from 7 to 3, And the right subarray will be number 2 that we have here. And we can do the same thing for this right subarray that we have here. So the lower index is equal to, and this is equal to 3. Okay, because 9 is at index 3 and high index is equal to 5. So together will be 8. 8 divided by 2 gonna be 4. So the middle index will be number 4. So my first subarray will be from index 3 to 4, that is 9 and 4, and the other subarray will be from 5 to 5, that is only number 8. Okay, so here look at number 2 and number 8 here. As you see, they cannot be broken down into smaller subproblems because we only have one number, and one number is already sorted. So if we have an array of size 1, okay, it's always sorted, okay, because there's no other number like to compare that number that we have in the array of size 1, so it's already sorted. So that's when we are stopping going like and breaking down the subproblem, or where we are stopping calling the recursive function of the merge sort, that is breaking the problem into subproblems. But the 7 and 3 here in this subarray and 9, 4, the other subarray, still they can be broken down into smaller pieces. So here again, if we break down this array subarrays, we will have 7 and 3, and here we will have 9, and here we will have 4. So here 7 and 3 and 2, 9, 4 and 8, okay, they are sorted, and we cannot break down into smaller pieces. So let's get rid of these values here. Okay, and now, so we have two subproblems that are already sorted. Now that's the time for merging the solutions. So we have number 7 and number 3. So that's how the merge part works. So you're comparing the number at this first subarray that starts as index I, let's say index I, and we have another like the right subarray that have the index j. So we are using index I for the first subarray and index j for the second subarray. And anytime that we are going to merge them, okay, we are increasing I and j based on from which array subarray we are choosing the value. Another index that we need to use is the index k. That is for the merging subarray. So because these are two subarrays, we need to have another array that is from the size 2 that keeps the sorted subarray. So first, I is equal to 0, j is equal to 0, and also k is equal to 0. So we are comparing the item at location I of left subarray with the item at location j of the right subarray. And because 3 is less than 7, so first we are moving this 3 to the merge array at location k. And that in this case will be number 3. So we have number 3 here. Then we are increasing j. So j becomes 1, and now we are because we are done with the j. Okay, there is no more items in j that can be compared with the left subarray. We are moving everything that we have from the left subarray to the right to the end of the array that have the index k. So also number 7 will go here. So as you see here, we have 3, 7. They are already sorted. Okay, so that's part of the subproblem. Now the next part is we have number 2, this subarray that's already sorted, and subarray 3 and 7 that is already sorted. Again, here for this subarray we'll have I and j. For 3 and 7 we have I that is equal to 0. Also for number 2 here we'll have j that will be sorted from number 0, and k again is 0. First we are comparing number 3 that is left array at location I, and the second subarray location j that is at location 0. Because 2 is less than 7, less than 3, so we are moving to to here, to the merge subarray, and increasing j. So j will be 1 now. And because right subarray doesn't have any other item, we are appending all the values from the left subarray to the right subarray. So 3 goes here, and also 7 goes here. And as you see, we almost sorted like the first subarray of the final array, that is array A. Okay, now let's go to the right part, and here we have 9, and we have 4, and we have 8. Okay, so doing the similar thing, we'll merge the 9 and 4 subarrays. So first we'll have 4, and then we're gonna have number 9. Here we have 8, and we have 4, and 4 is less than 8, so 4 goes here. So let's also relate I and j for this case. So I was 0, j was 0, and k was also 0. But because 4 was less than 8, okay, so we are increasing I, so I becomes 1, and also k becomes 1. Now we are comparing left subarray at location I, that is the location 1, that is equal to number 9, with the item allocation j of this right subarray that is equal to number 8. And because 8 is less than 4, so we are moving 8 here, and the k becomes 2, and j also becomes 1. And because there is no other item in the right subarray, we are appending all values that we have from the left subarray to the merge subarray. So we will gonna have number 9 also here. Then if you look at the our solution so far, you see that we have 2 sorted subarrays of the original array A. We do the same thing that we did for creating these subarrays. So again, we just start with values I equal to 0, j equal to 0, and also k equal to 0. So I's left subarray location I is equal to 2, and right subarray location 0 is equal to 4. And because 2 is less than 4, so we are moving to here. So 2 goes here. And now we're increasing I, so I becomes 1, also k becomes 1. Now comparing 3 with 4, and 3 is less than 4, so we are writing 3 here, and again we are increasing I, and we are increasing k. But there is no change in j because we haven't put the number 4 in the final solution yet. So now we have number 7 and we number 4, and because 4 is less than 4, we are putting 4 here. So increasing j, and again still increasing k. And k, as we said, this is the index for the final solution. So that's why no matter if we are choosing from the left subarray or the right subarray, we are still increasing k. Now we have number 7, that is at location 2 of the left subarray, with the item location 1 of the right subarray is 8. And because 7 is less than 8, so we are putting 8 here, and now I becomes 3. And because there is no more item in left subarrays, okay, so we are appending all the values from the right subarrays to the final solution. So that is adding number 8 and 9, okay, in the same order we had the final solution. So as you see now, the array is sorted. We have number 2, 3, 4, 7, 8, and 9. Okay, so that's the merge sort. Okay, and we are going to talk about the time complexity of merge sort. Okay, let's talk about the time complexity of merge sort. So here, going back to our example that we had of array of size n, that here in this case n is equal to 6. So as we said, we are almost dividing this problem into 2 equally sized subproblems. So here we have, let's say call this n1, so it's equal to 3, and also in this n2 equal to also 3. So if we have the time complexity of merge sort for an array of size n, then we are going to solve these 2 subproblems that are almost on the half size. So it's going to be twice the time complexity of solving the problems of the half size, plus we are gonna like do the merging these numbers, and because there is n divided by two numbers on the left subarray and n divided by 2 on the right subarray, so together the time like the number of operation will be from the theta of n. So, and if we use the massive theorem for solving this, we're gonna see that this is gonna be from the big O notation of n log n, both for the worst case and also the average case. So as we see, merge sort has a better complexity compared to bubble sort, insertion sort, and selection sort. The only thing that we need to consider when we are using the merge sort is the space complexity. Okay, because we are using auxiliary array for sorting, for merging the arrays, the sub arrays. Okay, then we also sometimes space that required. And the space complexity for the merge sort is from the big O notation of n, because at the end that's going to be the number of the memory that we need to have for merging the final array. That's going to from the big O notation of n. So the space complexity, okay, is going to be big O n, and the worst average case of the time complexity will be the big O n log n. So that's for today about merge sort.